Hello and welcome. In this video, we'll be introducing some foundational ANOVA concepts that'll become as important as we work through the rest of these lecture notes. So first of all, what is ANOVA? Now, we briefly introduced it in the previous lecture video to discuss the experimental design and how that related to the concept of ANOVA. But ANOVA stands for Analysis of Variance and is used to compare multiple population means. Think like a t-test, but now we can handle two or more groups instead of just having two different groups to compare. Analysis of variance, or ANOVA, essentially changes the approach that we take towards assessing these differences by, rather than analyzing differences between means, analyzing the variability between means, which we'll discuss more. We can use this test whenever we have one or more categorical independent variables and a continuous dependent variable. I say one or more categorical independent variables as, while through most of this lecture set we'll discuss the case with one categorical independent variable, you can do it with multiple categorical independent variables. And when we get to the two-way ANOVA section, we'll discuss how we can account for two or even more categorical variables in our analysis, which really opens up some analytical options. So consider a couple of different examples where we might utilize this ANOVA analysis. Maybe we want to compare several different brands to one another to determine the best quality of brand. Perhaps we want to look at several different marketing methods to determine the best return on investment for each of the different methods. Or maybe we want to examine several different policies to see which one reduces employee burnout. All of these are examples where we might have multiple options that we're considering between. And in that case, we may want to consider more options than just two. We might want to do this for a couple of reasons. One might be cost, another might be pragmatism, but a big one is just time. Why only consider two when I could consider three? That is to say, we shouldn't let our analytic method limit our practical design unless we just don't have the analytic method to address it. So by learning this new analytic method, we simply open ourselves up to more potentially efficient designs. For example, if I'm comparing four brands, that would involve multiple different pairwise comparisons. 1, 2, 3, 4, 5, 6, 7 different pairwise comparisons. So I could run 7 different studies to compare between each pair of two things, or I could run a single study and do my analysis with all four together. Note that in each of these examples, using some of our terminology that we discussed previously, the independent variable is going to be a categorical independent variable, or factor, with several different factor levels. So for example, we might have a brand of battery, and maybe I have Duracell and Energizer that I'm comparing. Our hypotheses in ANOVA can be phrased in a couple of different ways. So I can do this either using words or using equations. For me, it's a little bit more common to write it out in terms of words, and I think this is going to be a little bit less intimidating for you. So I think that's going to be a general expectation for us, and I'll show maybe a slight difference where your book might write one of these in terms of equations, a specific form. In words, though, the null hypothesis is simply that the averages or means for all of the different groups, that is, the factor levels, are the same. So if I'm thinking of the factor being battery brand and the outcome, say, the dependent variable being the life of the battery, then what I'd say is the average life of the battery, the mean of the outcome for each group factor level, that would be maybe Duracell versus Energizer, are the same. The alternate hypothesis simply states that at least one group mean is different from at least one other group mean. Now, in the case where we have 3 or more comparisons, what this will indicate is that one of the pairs is different, but we don't know which pair or contrast is different. So this is a problem. You'll see in the top of our lecture notes here, the term post hoc comparisons. That's a separate methodological technique used to determine which pairs are different. But in the main ANOVA analysis, that examination is not included. In the main ANOVA analysis, we just look at, is any of the means different from any other of the means? And end with yes or no. And if the answer is yes, again, it in the regular ANOVA analysis just stops there. In equation form, we can look at the null hypothesis as mu sub I equals mu sub j upside down a, which stands for all I not equal to j. So the means are the same over all i's and j's. Another way to potentially write this is mu sub 1 equals mu sub 2 all the way out to the final group mu sub capital I. And you'll note actually built into here is a bit of notation. We'll talk about this in a moment, that capital I is the total number of groups that we're going to be comparing. That'll be the notation for the total number of groups. If I remember right, your textbook uses that second equation for the null hypothesis, and then it uses the alternate hypothesis in words, and that's how they build it out. At least one group is different, and then for the null hypothesis, again, it just writes out mean of group 1, mean group 2 equals mean of group 3 equals mean of group 4, etc. The alternate hypothesis in equation form simply says backwards E, that stands for there exists a pair of I and j, colon, that stands for such that. So there exists a pair of I and j such that the mean of group I is not equal to the mean of group j. That is, there's at least one pair of groups that have different means. Note that here for the null to be rejected, any two means can be different. And again, this doesn't tell us which ones are different. I'd call this a limitation with ANOVA, but there's very standard practices to follow up with this if ANOVA is significant. That is, if we determine to reject the null hypothesis, reject or cross out the belief that all means are the same in favor of the belief that at least one group is different, there's standard methods by which we can follow that up to determine, okay, well, which group is different? And we'll discuss those. So the strategy here has to change a little bit, and this is because with the t-test, we took a difference between the two means we were comparing. But with more than two groups, this is more difficult. We can't just take a difference between all of the means. It's kind of a weird concept, and that difference doesn't necessarily mean anything. So the approach we're going to take is this. We're going to compare the variance between the groups, called the treatment or signal. Signal is more machine learning language, so don't worry about that, to the variance within the groups called the error or the noise. Maybe the nice thing to think about with signal and noise is to think about an old-timey TV setup where you had a TV signal coming in and then you had white noise. The goal is to determine if the TV signal is stronger than the white noise. So are the images I'm seeing just random white noise coming together to make a funny image? Or is that the actual signal of the underlying TV? And that'll depend on how strong the TV signal is. And that's in comparison to how strong the white noise is. So we're eventually going to compare the between groups variability to the within groups variability. Now, I'll say, when I say variance between groups, I literally mean if you think of like a box plot of three groups, the variance between groups literally looks at the means of the three groups and calculates the variance of those three numbers. That's the variance between the groups. If you think about group means that are all really close together, it's going to have a pretty small variability. But if group means are really far apart, it's going to have a really large variability. And that's the idea. For group means that are far apart, that implies that there's more evidence that they're different. And so that between groups variability, or that signal, TV signal, is going to be large. So if we're looking for a difference between groups, or hoping we're going to find one, want the groups to be far apart. And in our t-test, we just subtracted them. But when we've got multiple groups, essentially what we do is we look at the variance and say if the variance is high, that means that the values are far apart. So for the between variance, the values are the group mean, and that's far apart. if the variance is high. For the within groups, think about not the means of each of the different, say, the hypothetical box plots, the averages I'm showing on my hands here, but think about if I had a box plot down here, how wide that box plot is. So if I'm comparing two box plots and within each box plot is pretty narrow, then the difference between the box plots is pretty clear. It's pretty clear group A is different than group B. But if within the box plot is really, really wide, because there's a lot of overlap, it's not necessarily clear that group A is different than group B. So when we talk about variance between groups, realize that we're literally talking about group A, group B, and group C, and the variance of their means. When we talk about the variance within groups, realize that we're literally talking about the movement, or the literally calculated variance, of the data points inside of each group. That's what we're talking about. So all our statistical tests are trying to tell us, did the group differences happen because of the difference in the levels of the independent variable, or did they just happen by chance? If there's a reasonably probability that it happened by chance, then we're not going to change our mind and determine that it was the independent variable that caused it. But if we do have strong evidence that it happened by more than something just chance, that is, that the groups are actually different, or that the factor levels, Duracell versus Energizer, are actually different in their battery lives, then we would change our minds and say, okay, we went in assuming that there's no difference, and we've changed our mind to now believe that there is one. All right, so I actually drew out some of the graphics that I've been trying to kind of show you on my little camera here. So you got to see me pantomiming these, but now you can see actual graphics. Here's a graphic where you can see a relatively large variance within and a relatively small variance between. You'll see that there's a lot of overlap between these pictures, and these pictures may not offer convincing visual evidence that these groups are different. Note that, again, we can get into debates about is it significant or borderline, or maybe group 1 versus group 3 is just different enough. That's not really what I'm talking about here. What I'm talking about here is something a little bit more intuitive, and we'll get into the details later, I promise. But on an intuitive level, these just have a lot of overlap, so I'm not really convinced that there's a lot of difference between them. Note again the characteristics of this. The separation of the thick black line in each of the three graphs is relatively small compared to the width within each of the boxes. Each of the boxes has a pretty wide width in comparison to the spread, or each of the boxes individually has a pretty wide spread in comparison to the difference, or the spread, of the means of the black lines. Let's compare that with a different graph. The spread of the means in this, now it's zoomed in a little bit, but they're mathematically the same, and the spread shows a little bit better when we zoom in, largely because the width within the boxes has now shrank drastically. So because of this, we can feel a little bit more confident that these groups definitely seem to be different. Why? Well, essentially because when we look at the difference in the black lines, those are larger than the spread within each of the boxes. So when you think about between and within and what ANOVA is trying to do, the goal in ANOVA is to use this visual evidence and essentially say, this is an evidence of a large variability between relative to the amount of white noise or variability within. And the previous graphic is an example of a lot of variability within compared to relatively low variability between the groups. The movement between the groups wasn't very much, and there was a lot of movement within the groups. Here, the movement between the groups looks really large in comparison to the movement within the groups. So in this one, we would expect to hopefully see a more statistically significant, or closer to statistically significant, ANOVA test, indicating that this one has more evidence that the groups are different than the previous one. That's what we're trying to accomplish via images, is to capture this one as, more different than the last one using numbers. So a big piece here, because we're going to talk about variance within and between throughout this lecture set, is that when I say variance within and variance between, that's exactly what I mean. Within, inside each of the groups, and between each of the groups. Variance within is the variability within the group. And I will say, because we have variability in each group, it's worth noting that we're going to take the variance in group 1, group 2, group 3, and eventually add all of those together. And actually, I think in our shorthand equation, that is quite literally what we do. Variance between, this is the variability between each of the groups. So we're going to look at the variance in the group means. And so when we talk about variance within, variance between, or you'll hear the term sum of squares within, sum of squares between, we'll get there later in this video. When you hear those things, realize that I literally mean within, inside of each group, and between, meaning between the different groups. So again, the goal for data with relatively large variability between, that is, the group means are relatively far apart compared to within, you'd see a larger gap between the boxes, and vice versa. For this type of situation where you see a larger gap between the boxes, we'd like it to be closer and closer to significant, or more and more statistically significant. That is, we'd like the numbers to reflect that there's more and more evidence that the groups are different. So this is the foundational concept. How do we actually do the math or write the equations to represent that visual concept? Well, this is going to require some new notation, and I'll be honest, this notation, there's a fair amount of it. This is probably the most notation heavy that we're going to be in this course, is this chapter. So bear with me. The first notation is I, where it previously represent the person in the sample. So I equals 10, represent person 10. In this notation for ANOVA, I is going to represent the group counter. So I of 3 will mean group 3. I will go from 1 to capital I, and capital I will be the total number of groups that we have. J is another iterator we're going to use. This is going to be the counter of the observation, so like the 10th person or the second person. This is going to go from 1 to capital J being the total number of people within each group. And I'll quickly note, and this will be good to write down in your notes, sometimes instead of capital J, you'll see the notation lowercase n. Again, lowercase n in that other notation representing the total observations within each group. So just be aware that sometimes that notation is there. It's worth noting that for the observation counter, this is the observation within each group. What do I mean by that? Well, group 1 is going to have its own j equal 2, and group 2 is going to have a completely different j equal 2. So we're going to have a quote-unquote second person, j equals 2, in each group. So j goes from 1 to capital J for each group differently. So for instance, I might get an observation that is I equals 5 and j equals 3. That represents the 5th group and the third person within the 5th group. And then I might get an observation that's I equals 2 and j equals 3. It's still j equals 3, but now we're talking about the third person in the 2nd group, not the 5th group. So that represents a completely different person. That is to say, I need to know both I and j to identify a particular person participating in the study. Y is going to represent the dependent variable, the outcome variable. In our battery example, we had 2 different batteries, and then we looked at the total number of hours that they lasted. So Y would be the hours that they lasted. For any particular record, Y sub ij represents that outcome variable for the ith group and the jth person in that group. So for example, Y42 would represent the 4th group and the 2nd person or observation in that group. I guess I shouldn't say person when I'm using a battery example, but hopefully I'll get the feel for it. Y sub I dot bar is a very fancy way of saying the average of the ith group. So you'll see Y sub 2 dot bar. That just means the average of all the outcome values in the 2nd group. So the bar, Y bar, means the average of Y. The I part indicates which group it's from, and we put a dot there because if I take the average of group 2, I'm not talking about any single individual of group 2. That would be where J is. I'm talking about essentially all of the observations in group 2. So we put a dot in the place of J to represent that we're looking at all of the J's. So Y sub I dot, that is, I'm looking at group I, all of the J's in group I, and then the bar indicating I'm taking the average of that. Now, similarly, we have Y dot dot bar. I'm looking at the average, Y bar, dot for the I's, indicating all groups, dot for the J's, indicating all observations. So this is the mean of all of the observations in all of the groups, all at the same time. Sometimes this is called the grand mean, and essentially how we find this is we take all of our data values together and we add them all up and divide by how many total we have. Now that total sample size of all of the participants in all of the groups put together is sometimes denoted capital N. One last thing to remind you is the summation notation. So for the summation notation, if I do that capital sigma, that means to add everything up. And this will become important because now we have I's and J's. We have two different subscripts. If I see this first summation notation, I equals 1 to capital I, that means that I'm adding over all of the groups. I'm adding up whatever's in parentheses after the summation notation for all of the groups, all of the I's. I'll shorten this sometimes to summation over I, and that just means that I'm adding up all of the groups. So I might not write I equals 1 to capital I, but that still indicates the same thing. All right, so that's actually all of our notation. But before we can move on with our ANOVA, there's actually a very important foundational concept that we need to cover. Essentially, what we're going to discuss is the movement formula. So this is kind of like the inside of a variance. If you remember your variance equation from your previous course or the review, the variance was any data point minus its mean squared. And then we add it up and divide by how many we have. But the core of that is the movement between the data point and its mean, the data point minus its mean. So the basic movement is just the data point, y sub ij, that is for any particular group, any particular individual in it, minus the total mean. Now, what we're going to do is we're going to break down this movement formula into two different components. So I'm going to add a special 0, minus y bar, yi dot bar, plus yi dot bar. And remember, if I have a minus and a plus thing together, those are 0. So I'm adding 0. That doesn't change anything. I promise, nothing up my sleeves. But I'm going to put it in the middle, right after the yij. So I'm going to do yij minus yi dot bar plus yi dot bar minus y dot bar. So I'm adding a special 0 in the middle. What this is going to do is it's going to let me re-express this expression in a way that isolates the different components that go into that variance. So specifically, to highlight what we're talking about, I'll put parentheses around the beginning and end. Now, all of this is the same order of operations, so the parentheses doesn't matter here in terms of the math, but it does help to visualize what we're discussing. What we have here is yij minus yi dot bar. This is the distance between any point and its group mean, that is the mean of group I. Then I have yi dot bar minus y dot bar. This is the distance between the group means and the grand total mean. This equation gives rise to this concept that the total movement in data can be broken down to the movement within a group, that is the data point's distance from its group mean, and the movement between the groups, that is the group mean's distance from the grand mean. Essentially, this is the movement equations and the components of movement that relate to the visual component that we were talking about earlier, where we wanted to assess the difference between the movement between the groups and the movement inside of each group. Now, it's worth noting here that the variance involves squaring these terms. So we have to take a sum of squares, or we have to square these things and add them up. Now, if you remember anything about squaring, you'll remember that if I square the stuff on the left, that doesn't necessarily equate to squaring the stuff on the right. Because if I square the stuff on the left, if I square the stuff on the right, in the addition sign, well, now I've got to do some weird, like the first term squared plus the second term squared plus 2 times the first term times the second term. So it doesn't actually nicely mathematically work out. What's cool, though, is though it takes a bit to prove, it actually does nicely mathematically work out in this case. If I look at the addition over all of the groups, over all of the people, for each of these terms squared on the left side and squared on the right side, this actually does mathematically work out such that the sum of the squares for the total movement is equal to the sum of the squares within each group plus the sum of the squares between each group. Now, this might seem like a subtle thing, and you're like, hey, Dr. Florin, you just added sums and squares, and you're not necessarily wrong in the sense that in terms of the writing, I just wrote a little bit more. But in terms of the mathematics and the logic flow, this is actually not an expected result. This is something that's somewhat counterintuitive. And it does take a little bit to prove this. It's not impossible. It's not even necessarily difficult. It might take 5 or 10 minutes. But it's not necessarily straightforward or given either, as simple as it seems. So this is actually kind of cool. And this is a really, really big piece. We have it here. This is called the fundamental ANOVA identity. And this is what forms the foundation of how we calculate the analysis of variance. What this bottom thing says, and when you see sum of squares, think that this is a component of our variance. So these are kind of the variance component terms. This is the total variance component on the left-hand side is equal to the variance component inside of each group plus the variance component between each of the groups. That is, I can break down the total movement in data into just 2 pieces with nothing left over, the movement inside each group and the movement between the groups. And that's the whole concept behind what our ANOVA analysis does. Now, when we do the analysis, we actually have to do those calculations, and then we have to do more calculations on top of that. So we actually have to do a fair amount of work in order to get the results of an ANOVA. To keep all of that work straight, it's common to present your work and results in a table form that's called, for this analysis, the ANOVA table. We now have all the pieces that we need to put this together. And I'll say the critical value that we're going to use for this eventually is going to be the F distribution, the same one that we talked about when we analyzed the ratio between 2 variances. And again, as we're talking about comparing the between variability to the within variability, the fact that we're using a distribution that's created and we used for comparing 2 variances might maybe make a little bit of sense. So for the ANOVA table, this is what an ANOVA table looks like. In the left-hand side here, we have the source of variability. So just follow me through as we talk through each of the different columns and take a deep breath and don't stress about this too much. In the left-hand side, we have the source of the variability. The first component is the sum of squares between, or the between source between groups. Sometimes this is called treatment. The second one is called the within, and that is the variability within the groups. And then last, we have total variability. And I'll say in the R software, total variability in the ANOVA table is not displayed. For the sums of squares, we have the sum of squares between plus the sum of squares within equals the sum of squares total. That's what we had in our previous slide. That's our fundamental ANOVA identity. And so each of those pieces, we actually already have the equations of. Now I write TR, E, and capital T here to represent treatment, error, and total. Again, another thing you see. But the notation could just as well be, and I think I mentioned this here, SSB instead of SSTR, SSW instead of SSE, and SST is very common for total. So just note that there's two different notations here, and they're both commonly used. Sum of squares treatment, sum of squares error, sum of squares total, or sum of squares between, sum of squares within, sum of squares total. I will say later in the course, we'll use SSE a little bit more often. For the degrees of freedom, each of these components, the between, the within, and the total, each have their own degrees of freedom. And I can't remember if we mentioned this on the next slide or not, but I'll say that the degrees of freedom for the between, or treatment, plus the degrees of freedom for within, or error, equals the degrees of freedom total. So if I have two of these, I can always find the third one using, just a little math and fill in the blank. For MS, the column stands for mean squares, and this is essentially where we calculate the variance components. Remember, a variance, when we did the variance by hand, we summed the squares and then we divided by n-1, say. In our case, the n-1 component is going to be the degrees of freedom. And so we're going to sum the squares and then divide by the degrees of freedom to get that variance piece. Now, I don't indicate it here, but mean squares is typically denoted MS. So the SSTR divided by the DFTR would equal MS, mean squares TR. And that would be the notation we would use. Similarly, for the error, the sum of squares error over the degrees of freedom error give me the MSE, or the mean squared error. And again, that MSE is a term that'll pop up a lot when we get to the regression chapter. In here in ANOVA, feel free to use MSB or MSW. Again, those are very, very common notations in ANOVA. Both of these are common, so I kind of struggle with how to present these and try to present them both ways. I know that's a little bit confusing, and I don't like presenting multiple notations in class, but the truth is both of these are extraordinarily common. SSB, SSW are probably a little more common in ANOVA, but because we'll see SSE and MSE later in the course, I think that's why I put that on these slides here. For the F distribution is just the ratio of the two variance terms, or the two mean squares. So I'll take the mean squares between divided by the mean squares within, or in this slide's notation, the mean squares treatment divided by the mean squared error. And that's my F statistic. I'll say we don't really calculate the mean squares total, or F for error or total, because the whole point is to calculate the test statistic to run the test. All of this is information necessary to run the test, and so all I need to find the F statistic is the ratio of the two mean squares. I just have to divide them. And so because I only need those two, I don't then calculate the mean squares for the total, because I'm not going to use that at all in my calculation for F, or the p-value. I just need the mean squares treatment and the mean squared error, or the mean squares between and mean squares within. And again, the F is the mean square between divided by the mean squared within, or if you're using the other notation, as is on the slide, the mean squared treatment over the mean squared error. The p-value is the same p-value as we've always done for the F, so it's the same kind of one that we did when we were comparing two variances. So the p-value is that same calculation. I'll say, though, when we're looking at the degrees of freedom, remember the F distribution needs 2 degrees of freedom. Remember where those come from. The degrees of freedom for the numerator, in this case, DFTR or DFB, and the denominator is the error, degrees of freedom error. And so for the F distribution, the first degrees of freedom will be the degrees of freedom from the treatment, DFTR, and the second degrees of freedom will be the degrees of freedom for the error. So that's where we're going to get the degrees of freedom for this F distribution for both the critical values and the p-values, depending on what approach we're using. So again, the SST, SSE, and SSTR, SSE and SST, that's the sum of squares treatment, sum of squares error, and sum of squares total, respectively, and you can write those in. Remember, SS treatment is the same as SSB, or a sum of squares between. SS error, SSE, is the same as sum of squares W, or a sum of squares within, and SS total is still SS total. But if you go back to that fundamental ANOVA identity that we saw a couple of slides ago, the sum of squares total, sum of squares within, and sum of squares between were all given, and those are the equations for those terms in the ANOVA table. The degrees of freedom we haven't talked about yet. The degrees of freedom for the treatment is capital I minus 1. And remember, capital I is the total number of groups. So for the treatment, or DFB, if you're using that notation between, I take the total number of groups and subtract 1. For DFE, or again the other notation, DFW, for the this component, the degrees of freedom, I take capital I times, and then in parentheses, j minus 1. So remember, capital I is the total number of groups. Capital J is the total number of observations within each group. So I'll note this assumes that the total number of observations within each group are the same, because if they're not, capital J would depend on which group you're in. So assuming we have the same number of observations within each group, the degrees of freedom for the error is capital I times capital J minus 1. Now, it's important that you do the J minus 1 first before multiplying so you don't get the wrong answer. So for instance, if I had 3 groups and J, let's say the number of observations in each group is 10. So 3 groups of 10, 30 total people, 3 groups of 10 each. Capital I would be 3, capital J would be 10. Because J minus 1's in parentheses, I would first do the 10 minus 1 to get 9, and then multiply by capital I, in our case 3, to get 27. So it's important you do the J minus 1 first before multiplying to find your degrees of freedom error, or again in the other notation, degrees of freedom within. For the degrees of freedom total, you do the same thing, except you don't have the parentheses. So you take I times J minus 1. It's worth noting I times J, capital I times capital J, gives you the sample size. So if capital J is the total number of people in each group, in our previous hypothetical, that would be 10 people in each group, and capital I is the total number of groups, in our previous hypothetical, 3, capital I times capital J, 3 times 10, gives me the total number of people in the study, capital N, or in that case, 30. If I have 3 groups of 10 people, there's 30 total participants in the study. Degrees of freedom the degrees of freedom total is simply the total number of participants minus 1. You can find that using capital I times capital J minus 1 with no parentheses. You do the multiplication first before subtracting 1, or you can find that by taking the total number of participants, capital N, and subtracting 1. So remember, MS stands for the mean squares, and it's calculated by taking that total sum of squares and dividing by its corresponding degrees of freedom. The F statistic is the ratio of the 2 mean squares. So we take the mean squares from the treatment. Again, you can write between there if you want, and divide by the mean squares error. And again, you can write within there if you want. And it looks like I write it there here too. Mean squares between over mean squares within. And that's that's just a different notation of saying mean squares treatment over the mean squares error. So just like before, again, once we have the test statistic, I can either compare it to a critical value to determine my decision, or I can calculate a p-value depending on what I want to do. If I do use the p-value approach, it is common to include the p-value in the ANOVA table. So if you choose not to use the p-value approach, that p-value column in the ANOVA table is usually not included. But if we do the p-value approach, it's usually included. I think I've mentioned this previously in this course, but the p-value approach is very common in applied research for a couple of reasons. The main is it's a little bit interpretationally simpler when dealing with a whole ton of different tests and test statistics and critical values and stuff like that. It's a lot easier to just look at one p-value with one decision rule. So p-values are very common, and software will tend to output them by default. But if you ever do one by hand and are presenting those results, you wouldn't include the p-value column in the table. You would just compare to the critical value. And if you do use the p-value or calculate it, you would include it in the table typically. All right, so again, I mentioned in the fundamental ANOVA identity slide, these are kind of the equations for those different components, but there are some shortcuts if you want to take some shortcuts in the calculations. So for the sums of squares shortcuts, the sum of squares treatment can be shortcutted as capital J, that's the total number of observations in each group, times the sum of y sub I dot bar minus y sub dot bar quantity squared. That is, for each group, I'll take the group mean minus the grand mean, then I'll square those and add them all up, and then I multiply that sum by the total number of observations in each group, and that's my sum of squares treatment. A shortcut formula if I'm doing this by hand. For the sum of squares error, I'll take capital J minus 1, that's the total number of observations in each group, subtract 1, and then I'll find the variances for each of the groups. So remember, S squared is the sample variance in each group. So I'm going to find the sample variance for, remember, I stands for group now, sample variance for group 1, sample variance for group 2, sample variance for group 3, inside the group. So this is the variance within the group. And then I literally add them up. So remember, SSE, the other notation is SSW, the sum of squares within. And I mentioned when we were talking about the fundamental ANOVA identity and the concept that we were going to add up all of the variance inside. We can see here, we literally are adding up the variances from within each group. So I go to group 1 and I calculate the variance. I go to group 2 and I calculate the variance for only people in group 2. And then I add up all of those variances and multiply by J minus 1. For the sum of squares total, this equation looks kind of yucky, and it kind of is. You would take each of the data values squared and add them all up. That's on the left-hand side, that sum over I and sum over J of y sub ij squared. That's just taking all of the dependent variable values that you have, squaring them, and adding them all up. The second thing is you add up all the dependent variables, and then you square after you add them all up. So on the left hand, you're squaring before you add them. On the right hand, in that numerator, you're squaring after you add them. Then on the right-hand side, you divide by the total sample size. That is your capital I times capital J, or just the total number of participants you have in all of your groups combined. I'll mention if SSTR, or remember the other notation, SSB, and SSE, or the other notation, SSW, if those look easier, remember the sum of squares are additive. That's the fundamental ANOVA identity. So if I have the SS between plus the SS within, that gives me the sum of squares total. So you can do these first two equations and just add them to get the sum of squares total. And you can do the same thing with the degrees of freedom. Not that the degrees of freedom equations are particularly hard, but that can be really handy because sometimes these equations are a little bit more irritating. So for instance, it might be really easy to find the sum of squares treatment and the sum of squares error, and I'll just add those two together to find the sum of squares total. And again, treatment, error, between, within, sum of squares between plus sum of squares within gives me the sum of squares total. So I will say, while these shortcut formulas are kind of handy by hand, the previous ones are a little bit more intuitive. With that said, I quite like the sum of squares error one because it is pretty intuitive that we're literally finding the variance of each group and then adding up the variances of all the groups to get the sum of squares error. But the intuition I'm talking about with the fundamental ANOVA identity is the distance between the data point and its group mean and the distance between the group mean and the overall total. And that the total distance between the data point and the overall total, or the overall mean, can be broken down into those two subcomponents. So I do like that part of the previous equations. All right, ladies and gentlemen. Well, thanks for sticking with me through this video. And this has been a coverage in this video of the fundamental ANOVA concepts, things that you'll need to move forward in this lecture set. So we'll soon start to actually use them. So thanks for sticking with me through this video, and I'll look forward to catching you on the next one.